Have you ever wondered what lies beyond the point of no return, where even light cannot escape? Black holes, the enigmatic monsters of the cosmos, have fascinated scientists and dreamers alike for decades. From their mysterious formation to their immense gravitational power, black holes challenge our understanding of space and time. Join us as we dive into the incredible world of black holes and uncover their secrets, exploring the science, the wonder, and the unknown. The formation of black holes, the birth of a cosmic giant. Black holes form from the remnants of massive stars that have reached the end of their lives. As a star burns through its nuclear fuel, it maintains a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. When the fuel is depleted, gravity wins the battle, causing the star to collapse under its own weight. For stars much larger than our Sun, this collapse leads to the formation of a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape. The gravitational pull here is so intense that not even light, the fastest thing in the universe, can escape its grasp. Not all black holes are created equal. Stellar mass black holes are born from the death of stars, while supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of galaxies. These colossal entities likely formed from the merger of smaller black holes and the accretion of vast amounts of matter over time. Intermediate mass black holes, a middle ground between stellar mass and supermassive, have been harder to find, but their discovery has opened new avenues for understanding black hole evolution. Their formation remains one of the great mysteries in astrophysics, providing a link between the small and the colossal. The creation of black holes is a process that illustrates the immense power and complexity of the universe. From the remnants of dying stars to the titanic forces shaping galaxies, black holes remind us that even destruction can lead to profound new beginnings in the cosmos. The anatomy of a black hole, beyond the event horizon. A black hole is more than just an abyss. It is a complex structure with distinct parts that play a crucial role in its behavior and influence. At its heart lies the singularity, the point of infinite density and zero volume where gravity is so intense that it warps space and time to extremes. Surrounding the singularity is the event horizon, often referred to as the point of no return. Once an object crosses this boundary, escape becomes impossible. The event horizon is not a physical surface, but rather a mathematical boundary defined by the black hole's immense gravitational pull. Outside the event horizon, many black holes are surrounded by an accretion disk, a swirling mass of gas, dust, and debris drawn in by the black hole's gravity. As this matter spirals inward, it heats up to millions of degrees, emitting intense radiation that can be detected by telescopes on Earth. In some cases, black holes produce powerful jets of high-energy particles that shoot out from their poles at nearly the speed of light. These jets are powered by the intense magnetic fields generated by the accretion disk and can extend for thousands of light years, influencing the formation of stars and galaxies. Understanding the anatomy of a black hole reveals the intricate processes at work in these celestial phenomena. They are not simply voids, but dynamic and influential objects that play a pivotal role in shaping the universe around them. How black holes warp space and time. Black holes are more than gravitational traps. They are cosmic engines that distort the fabric of space and time. According to Einstein's general theory of relativity, massive objects like black holes curve space-time, much like a heavy ball placed on a stretched rubber sheet. As a result, time near a black hole slows down relative to an observer far away. This phenomenon, known as time dilation, means that a clock near the event horizon ticks more slowly than one in a distant region of space. If you were to observe an astronaut falling into a black hole, their movements would appear to slow down as they approached the event horizon, eventually freezing in place. The intense warping of space-time also affects light. Black holes can bend light paths, creating a phenomenon called gravitational lensing. This effect allows astronomers to see objects hidden behind massive celestial bodies, as light from distant stars and galaxies is bent around the black hole. At the event horizon, space-time becomes so warped that all paths lead inward. Once something crosses this boundary, it is destined to fall into the singularity. This extreme distortion of space-time challenges our understanding of the universe and raises questions about the nature of reality itself. By studying how black holes warp space and time, scientists gain insights into the fundamental laws of physics and the relationship between gravity, matter, and energy. Black holes are laboratories for testing the limits of our theories and exploring the universe's deepest mysteries. Black holes and the cosmic web. Black holes are not isolated entities. They are deeply connected to the large-scale structure of the universe. They play a central role in the formation and evolution of galaxies, often acting as the anchors around which galaxies grow. Supermassive black holes, located at the centers of galaxies, influence the motion of stars and gas in their vicinity. Their immense gravitational pull binds galaxies together, while the energy released from accretion disks and jets can regulate star formation by heating and dispersing surrounding gas. Galactic collisions and mergers often lead to the merging of black holes, creating even larger supermassive black holes. These events release powerful gravitational waves, ripples in space-time that can be detected by instruments like LIGO and Virgo. The relationship between black holes and the cosmic web extends beyond galaxies. The jets from supermassive black holes can shape the intergalactic medium, distributing energy and influencing the formation of galaxy clusters. Black holes are key players in the intricate interplay of forces that define the universe's structure. By understanding the connection between black holes and the cosmic web, astronomers piece together the story of how galaxies and the universe itself have evolved over billions of years. The Event Horizon Telescope. The Event Horizon Telescope, or EHT, represents a groundbreaking effort to capture images of black holes, allowing humanity to glimpse the unseeable. Using a global network of radio telescopes synchronized to act as a single, Earth-sized instrument, the EHT captured the first-ever image of a black hole in 2019. This historic achievement revealed the shadow of the black hole at the center of galaxy M87, surrounded by a glowing ring of hot, spiraling matter. The image was more than just a visual spectacle. It confirmed the existence of event horizons and matched predictions made by Einstein's theory of general relativity. The glowing ring represents light bending around the black hole, while the dark shadow marks the region where light cannot escape. This discovery offered direct evidence of how black holes warp spacetime and manipulate matter. The EHT's success was a culmination of years of collaboration among hundreds of scientists and engineers. Data collected from observatories worldwide was combined using a technique called very long baseline interferometry, enabling the extraordinary resolution necessary to image a black hole's shadow. Building on this achievement, the EHT is now targeting other black holes, including the one at the center of our galaxy, Sagittarius A*. These efforts promise to reveal even more about the enigmatic nature of black holes and their environments, providing a window into phenomena that were once purely theoretical. The Event Horizon Telescope has opened a new frontier in astronomy, proving that humanity can tackle the most daunting challenges in exploring the cosmos. It is a testament to the power of global collaboration and the unyielding human desire to uncover the universe's deepest mysteries. The power of gravitational waves. Listening to cosmic collisions. Gravitational waves, ripples in the fabric of spacetime, are one of the most exciting tools for studying black holes. First predicted by Einstein's general theory of relativity, these waves are produced by cataclysmic events such as the collision of black holes. In 2015, the LIGO Observatory detected gravitational waves for the first time, marking a new era in astrophysics. When two black holes spiral toward each other and merge, they release an immense amount of energy in the form of gravitational waves. These ripples travel across the universe, carrying information about the masses, spins, and distances of the merging black holes. Observatories like LIGO and Virgo capture these signals, allowing scientists to study cosmic events that would otherwise be invisible. Gravitational wave astronomy has led to several remarkable discoveries. It has revealed the existence of binary black holes, confirmed theories about their formation, and provided insights into the nature of spacetime itself. Each detection expands our understanding of the violent and dynamic processes that shape the universe. The study of gravitational waves has also opened the door to exploring the unknown. By observing waves from black hole collisions, scientists test the limits of general relativity and search for evidence of phenomena like primordial black holes, which may have formed shortly after the Big Bang. Gravitational waves are more than a breakthrough. They are a new way of experiencing the universe. They allow us to listen to the cosmos, unlocking secrets that were once hidden in silence and enriching our understanding of black holes and their dramatic lives. Black holes and the nature of information. Black holes present one of the most perplexing paradoxes in modern physics, the information paradox. According to quantum mechanics, information about the physical state of matter should never be destroyed. However, when matter falls into a black hole, it appears to vanish beyond the event horizon, seemingly erasing all traces of its properties. This paradox challenges the foundations of physics. Stephen Hawking's groundbreaking work on black hole radiation, known as Hawking radiation, suggests that black holes emit energy and can eventually evaporate over immense timescales. Yet this radiation seems to carry no information about the matter that formed the black hole, intensifying the puzzle. Physicists have proposed various solutions to the paradox. One theory suggests that information is encoded on the event horizon itself, much like a hologram. This concept, known as the holographic principle, implies that the universe's three-dimensional nature may be a projection of information stored on a two-dimensional surface. Another idea is that information may escape through subtle quantum effects during the emission of Hawking radiation. These theories are still being tested and debated, but they represent profound implications for our understanding of quantum mechanics, gravity, and the nature of reality. The information paradox demonstrates that black holes are not just astronomical objects, but philosophical and scientific challenges. They force us to reconsider fundamental assumptions about the universe, bridging the worlds of quantum mechanics and general relativity in a quest for a unified theory of physics. The ultimate fate of black holes. Black holes are not eternal. Over incredibly long timescales, they lose energy through a process known as Hawking radiation. This phenomenon occurs because of quantum effects near the event horizon, where particle-antiparticle pairs form and one falls into the black hole while the other escapes, carrying away energy. As black holes emit radiation, they slowly lose mass, shrinking over billions or even trillions of years. Eventually, a black hole will evaporate entirely, releasing a final burst of energy before disappearing. This process, though theoretical, has profound implications for the fate of black holes in the universe. In a far distant future known as the heat death of the universe, when stars have burned out and galaxies have dispersed, black holes may be the last remaining objects. Their slow evaporation will mark the final stages of cosmic evolution, leaving a cold, empty expanse. The study of black hole evaporation also sheds light on the interplay between quantum mechanics and gravity. Understanding Hawking radiation could lead to new breakthroughs in unifying these two fundamental forces, offering a glimpse into the underlying fabric of the universe. Black holes, born from the fiery deaths of stars, ultimately fade into obscurity. Their life cycle, from colossal gravitational monsters to evaporating whispers, symbolizes the incredible transformations that define the universe's story. They remind us that even the most powerful phenomena are not immune to the passage of time. The mysteries of black holes inspire awe and curiosity, challenging us to expand our understanding of the universe. From their formation to their profound influence on space and time, black holes are among the most fascinating phenomena in existence. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep uncovering the universe's secrets with us. Have you ever wondered what lies beyond the planets of our solar system? Beyond Neptune, a fascinating world of mysterious and lesser-known celestial bodies called dwarf planets awaits exploration. How are these worlds different from planets, and why do they captivate astronomers worldwide? Join us as we embark on an incredible journey to uncover the secrets of the dwarf planets in our solar system and explore their unique features and discoveries. Pluto, the trailblazer of dwarf planets. Pluto was the 9th planet of the solar system until 2006, when its reclassification sparked global debates. This icy world, located in the Kuiper Belt, is a fascinating dwarf planet that orbits the Sun over 248 Earth years. Despite being demoted, Pluto remains a captivating celestial body that continues to reveal secrets about our solar system. At 2,377 kilometers in diameter, Pluto is roughly two-thirds the size of Earth's moon. Its surface is a frozen expanse of nitrogen, methane, and carbon monoxide ice, with vast plains like Sputnik Planitia and towering ice mountains. Pluto also boasts a surprisingly dynamic atmosphere that expands and contracts with its elliptical orbit, showcasing how even the coldest worlds can exhibit complex weather patterns. Pluto's moon system adds another layer of intrigue. It has 5 known moons, with Charon being the largest and most remarkable. Charon's size, half that of Pluto, creates a unique relationship between the two, as they orbit a shared gravitational point. This binary system offers insights into how celestial bodies can evolve together in isolated regions of space. NASA's New Horizons mission, which flew by Pluto in 2015, revolutionized our understanding of this dwarf planet. The spacecraft sent back stunning images and data, revealing unexpected geological activity and potential subsurface oceans. These findings hinted that Pluto may harbor conditions suitable for some form of life, redefining what is possible in extreme environments. Pluto's story is far from over. As one of the most well-studied dwarf planets, it serves as a window into the mysteries of the outer solar system, demonstrating that even small celestial bodies can have monumental significance. Ceres, the smallest giant in the asteroid belt. Ceres stands out as the only dwarf planet located in the asteroid belt between Mars and Jupiter. Discovered in 1801, Ceres was once considered a planet before being classified as an asteroid, and finally as a dwarf planet in 2006. This unique classification underscores its importance in bridging our understanding of planetary and asteroid characteristics. With a diameter of about 940 kilometers, Ceres is the smallest recognized dwarf planet but holds massive scientific interest. Its surface is a mix of rock and ice, punctuated by bright spots like those in the Occator crater. These spots are deposits of sodium carbonate, a salt left behind by water activity. Such discoveries suggest that Ceres may once have had a subsurface ocean, and remnants of liquid water could still exist today. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed surprising geological features, including cryovolcanoes. Ahuna Mons, for example, is a towering ice volcano that indicates Ceres may still be geologically active. The presence of organic compounds on its surface also raises intriguing questions about the potential for prebiotic chemistry. Ceres' location in the asteroid belt makes it a unique laboratory for studying the building blocks of planets. Scientists believe it formed early in the solar system's history, preserving ancient materials that can provide clues about the conditions during its formation. As missions to Ceres continue to be proposed, this small world holds immense promise for unraveling the mysteries of planetary formation and the potential for life beyond Earth. Ceres is a reminder that size is no limitation when it comes to cosmic significance. Haumea, the peculiar oval world. Haumea is one of the most unusual dwarf planets, recognized not only for its elongated shape but also for its rapid rotation. This celestial oddity resides in the Kuiper Belt and is named after the Hawaiian goddess of fertility and childbirth. Its unique characteristics make it a captivating target for astronomers and planetary scientists. Unlike other dwarf planets, Haumea has a distinctly oblong shape, which is a direct result of its incredibly fast rotation. Completing a spin in just 4 hours, this rapid rotation has stretched Haumea into an oval, a phenomenon rarely seen on such a large scale. This unique shape provides insights into the effects of angular momentum on celestial bodies. Haumea is also notable for its composition. Its surface is largely covered in crystalline water ice, making it one of the brightest objects in the Kuiper Belt. This icy exterior hints at past collisions or geological activity that brought fresh ice to the surface. These impacts may also explain Haumea's 2 small moons, Hi'iaka and Namaka, which orbit it today. Another fascinating feature of Haumea is its ring system. Discovered in 2017, the ring adds to its distinctiveness as one of the few known dwarf planets with this characteristic. The ring likely formed from debris left behind by ancient collisions, showcasing the dynamic processes that shape the Kuiper Belt. Haumea's peculiarities continue to challenge and expand our understanding of dwarf planets. Its rapid rotation, unique shape, and icy composition offer a glimpse into the diverse ways that celestial bodies evolve in the distant reaches of the solar system. A Makemake, a frozen world with a fiery name. Makemake, named after the Rapa Nui deity of creation, is another Kuiper Belt resident that adds to the diversity of dwarf planets. Its icy surface and distant orbit make it one of the coldest known objects in our solar system, offering an extreme environment for scientific exploration. Measuring about 2/3 the size of Pluto, Makemake is the second brightest object in the Kuiper Belt. Its surface reflects a significant amount of sunlight due to a layer of frozen methane, ethane, and possibly nitrogen. These icy compounds contribute to its reddish hue, a feature that distinguishes Makemake from other celestial bodies. Despite its frozen nature, Makemake has shown signs of an atmosphere, albeit a temporary one. Observations suggest that its thin atmosphere forms when it is closest to the sun and freezes when it moves away. This cyclical atmospheric behavior provides clues about the volatile substances present on its surface. Makemake's moon, discovered in 2016, adds to its intrigue. This tiny satellite, informally named MK2, is a dark, rocky body that contrasts with the brightness of Makemake itself. The moon's presence offers scientists an opportunity to measure Makemake's mass and density more accurately, improving our understanding of its internal composition. Makemake's study is still in its early stages, but its unique characteristics make it a compelling target for future missions. As we continue to explore, this icy dwarf planet will likely reveal more about the dynamics and diversity of the outer solar system. Eris, the most distant dwarf planet. Eris, one of the most intriguing dwarf planets, resides in the scattered disk region of our solar system, far beyond Pluto. Its discovery in 2005 played a pivotal role in the reclassification of planets, including the demotion of Pluto to a dwarf planet. Named after the Greek goddess of strife, Eris lives up to its name by challenging our understanding of the outer solar system. Eris is slightly smaller than Pluto, but is the most massive dwarf planet discovered so far. Its high density suggests a composition rich in rock and ice, differentiating it from the gas giants that dominate the outer regions of the solar system. This composition aligns with theories about how icy bodies formed in the cold reaches beyond Neptune. One of the most fascinating features of Eris is its reflective surface, which rivals that of freshly fallen snow. This brightness is due to a thin layer of methane ice, indicating that it may have undergone surface renewal processes in the past. These observations suggest a dynamic history that includes the possibility of cryovolcanism or other geological activity. Eris is accompanied by a small moon named Dysnomia. This moon provides crucial data for calculating Eris's mass and understanding its gravitational interactions. Observations of Dysnomia's orbit allow scientists to estimate the density of Eris, giving insights into its internal structure and formation history. Eris's extreme distance from the Sun places it in one of the most isolated regions of our solar system. This distance poses significant challenges for exploration, but Eris remains a priority for future missions seeking to unlock the secrets of the scattered disk. Its discovery and study continue to reshape our view of the outer reaches of the solar system, demonstrating that there is still much to learn about the worlds beyond Neptune. Sedna, a mystery on the solar system's edge. Sedna, named after the Inuit goddess of the sea, is one of the most enigmatic objects in the solar system. Discovered in 2003, this distant dwarf planet resides in the far reaches of the solar system, in a region known as the Inner Oort cloud. Its extreme orbit and unique characteristics make it a key piece in understanding the early formation of our solar system. Sedna's highly elliptical orbit takes it on a journey that spans thousands of years. At its closest approach, Sedna is still over 76 astronomical units away from the Sun, nearly 3 times farther than Neptune. At its farthest, Sedna ventures nearly 1,000 AU away, a distance that places it among the most isolated objects in the solar system. With a reddish surface, Sedna's color suggests a composition rich in organic compounds. These tholins are likely the result of solar radiation interacting with frozen methane, ethane, and other ices. This composition points to similarities with Kuiper Belt objects, though Sedna's origin and migration remain a mystery. Theories about Sedna's unusual orbit range from gravitational interactions with a passing star to the influence of an as-yet undiscovered ninth planet. Sedna's orbit may also provide clues about the formation of the Oort cloud, a distant shell of icy bodies that surrounds the solar system and serves as a reservoir for comets. Although no missions are currently planned to explore Sedna, its study through telescopes continues to provide valuable insights. As one of the most distant known objects, Sedna represents the solar system's boundary and raises intriguing questions about the forces that shaped its formation billions of years ago. Quaoar, the forgotten jewel of the Kuiper Belt. Quaoar, a lesser-known dwarf planet, quietly orbits within the Kuiper Belt, adding to the complexity and diversity of this icy region. Discovered in 2002, Quaoar was named after a Native American creation deity, reflecting its status as a harbinger of new knowledge about the outer solar system. With a diameter of about 1,100 kilometers, Quaoar is smaller than Pluto, but still one of the largest objects in the Kuiper Belt. Its surface is thought to be a mix of water ice and other frozen compounds, suggesting that it may have had a more geologically active past. Observations of its surface have also detected methane, ethane, and possibly ammonia, pointing to a chemically diverse environment. Quaoar's discovery challenged traditional assumptions about the size and composition of Kuiper Belt objects. Its relatively large size and spherical shape highlighted the potential for even more massive objects in this distant region, sparking a renewed interest in exploring the Kuiper Belt's hidden treasures. One of the most exciting findings about Quaoar is the detection of Waywatt, its tiny moon. This discovery has allowed scientists to study the system's dynamics, providing clues about Quaoar's mass and density. The presence of Waywatt also suggests that collisions and interactions in the Kuiper Belt may have played a significant role in shaping these distant worlds. Although Quaoar remains underexplored, its significance cannot be overstated. It represents a bridge between the well-studied worlds like Pluto and the smaller, more enigmatic objects that populate the Kuiper Belt. As technology advances, Quaoar will undoubtedly remain an essential target for understanding the formation and evolution of the outer solar system. The search for Planet 9 and its dwarf planet clues. The quest for Planet 9, a hypothetical massive world beyond Neptune, has reignited interest in the outer solar system. Dwarf planets like Sedna, Eris, and others may hold critical clues to the existence of this elusive giant, as their orbits hint at the gravitational influence of an unseen force. The theory of Planet 9 arose from observing the unusual orbits of several distant objects, including dwarf planets. These orbits cluster in a way that suggests the presence of a massive, unseen body exerting gravitational pull. If Planet 9 exists, it could be 10 times the mass of Earth and orbit the Sun at a distance of hundreds of astronomical units. The study of dwarf planets is central to this search. Their unique orbits act as breadcrumbs, leading scientists toward the regions where Planet 9 might reside. By tracking these objects with powerful telescopes, astronomers can piece together a map of the gravitational landscape beyond Neptune. While the search for Planet 9 is ongoing, its potential discovery would reshape our understanding of the solar system's architecture. It would also provide context for how dwarf planets form and interact with larger celestial bodies. Dwarf planets could reveal how gravity sculpts the solar system's outer reaches and affects the distribution of smaller objects. Whether or not Planet 9 is ever found, the search highlights the importance of studying dwarf planets. These distant worlds are not only fascinating in their own right, but also serve as critical tools for uncovering the hidden secrets of our solar system. The dwarf planets of our solar system showcase the incredible diversity and complexity of celestial bodies beyond the 8 major planets. From Pluto's icy plains to Haumea's rapid rotation, these worlds invite us to explore and learn more about the cosmos. If you enjoyed this deep dive, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon for updates on our latest content. Until next time, keep reaching for the stars with us. Have you ever looked at images of Saturn and wondered about the magnificent rings surrounding this gas giant? How did they form? What mysteries do they hold? These shimmering bands are more than just a cosmic decoration. They're windows into the early days of our solar system. Are you ready to uncover the secrets of Saturn's rings and explore their fascinating role in shaping the cosmos? Join us as we dive into one of the most captivating mysteries of the universe. A cosmic masterpiece, Saturn's stunning rings. Saturn's rings are one of the most breathtaking sights in our solar system, capturing the imagination of astronomers and dreamers alike. These shimmering bands of ice and rock span an incredible width of over 175,000 miles, yet they're surprisingly thin, often no thicker than a few stories of a building. This delicate structure gives them their ethereal beauty and makes them a wonder of cosmic engineering. Each ring is made up of countless particles, ranging in size from tiny grains of dust to massive chunks as large as a small house. These particles are primarily composed of water ice, which reflects sunlight and gives the rings their dazzling appearance. Despite their apparent simplicity, the rings' intricate composition and structure continue to baffle and amaze scientists. The rings are divided into distinct segments labeled alphabetically, including the A, B, and C rings. Each segment has unique characteristics, such as variations in particle density and composition. For example, the Cassini division, a dark gap between the A and B rings, is caused by gravitational interactions with Saturn's moon Mimas, showcasing the complex dance of celestial mechanics. What's even more astonishing is the constant activity within the rings. Collisions, gravitational interactions, and the influence of Saturn's many moons create a dynamic environment where particles are continuously moving, clumping together, and breaking apart. This activity has helped scientists study the principles of planetary formation on a smaller scale, providing insights into how the solar system evolved billions of years ago. Saturn's rings aren't just a visual spectacle, they're a scientific treasure trove. Their unique characteristics and dynamic nature make them an unparalleled laboratory for studying the mysteries of planetary systems and the forces that shape them. The birth of the rings, ancient or recent origins. The origin of Saturn's rings has been a topic of intense debate for decades. Some scientists believe they formed alongside Saturn over 4 billion years ago, while others argue that they're a relatively recent addition to the planet's history. Both theories offer fascinating insights into the workings of our solar system. The ancient origin theory suggests that the rings are remnants of the primordial material that formed Saturn. In this scenario, the rings are made of icy particles that failed to coalesce into a moon, remaining in orbit around the planet instead. This theory aligns with the idea that the rings are as old as Saturn itself, providing a window into the solar system's early days. On the other hand, recent evidence from NASA's Cassini spacecraft points to a younger origin, possibly just a few 100 million years ago. This theory proposes that the rings were formed when a comet or a moon was torn apart by Saturn's gravity, scattering icy debris into orbit. The relatively pristine nature of the rings supports this idea, as they show little evidence of long-term contamination by interplanetary dust. Interestingly, both theories may be partially correct. It's possible that Saturn had older, primordial rings that were later rejuvenated by the addition of fresh material from a disintegrated moon or comet. This would explain the rings' youthful appearance while preserving their connection to Saturn's ancient past. Understanding the rings' origins isn't just about solving a cosmic mystery, it's also about unraveling the history of our solar system. By studying the forces that shaped Saturn's rings, scientists can gain a deeper understanding of the processes that created planets, moons, and other celestial bodies billions of years ago. Cassini's legacy, unlocking the rings' mysteries. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our understanding of the planet and its rings. Equipped with state-of-the-art instruments, Cassini conducted detailed observations that revealed the rings' stunning complexity and dynamic behavior. One of Cassini's most groundbreaking discoveries was the sheer diversity within the rings. High-resolution images showed intricate patterns, including wave-like structures caused by the gravitational pull of Saturn's moons. These waves act as a cosmic fingerprint, providing clues about the moon's orbits and the ring's composition. Cassini also uncovered fascinating details about the ring's mass and age. By studying how the rings scattered radio waves, the spacecraft measured their density and determined that they were surprisingly lightweight. This finding supports the idea that the rings are relatively young, as older rings would have accumulated more debris over time. Another remarkable discovery was the interaction between the rings and Saturn's upper atmosphere. Cassini detected a steady flow of material from the rings into the planet's atmosphere, a process dubbed ring rain. This phenomenon suggests that the rings are slowly disintegrating, and they may disappear entirely in a few 100 million years, a fleeting moment in cosmic terms. Cassini's final mission, the grand finale, involved a daring dive between Saturn and its rings. This maneuver provided unprecedented data on the rings' composition and structure, leaving behind a treasure trove of information for scientists to analyze. The spacecraft's legacy continues to inspire awe and curiosity, highlighting the value of exploration in unlocking the secrets of the cosmos. Shepherd moons, guardians of the rings. Saturn's rings owe much of their stability to a unique group of celestial companions known as shepherd moons. These small moons orbit near or within the rings, using their gravitational influence to shape and maintain the delicate structure of the bands. Each shepherd moon plays a specific role in the ring's dynamics. For instance, the moonpan carves out the Encke gap in the A ring, while Prometheus and Pandora work together to sculpt the edges of the F ring. These moons act as cosmic gardeners, clearing debris and creating striking features within the rings. The interactions between shepherd moons and ring particles are a perfect example of the delicate balance of forces in the universe. As a moon passes near the rings, its gravity pulls on the particles, creating ripples and waves that propagate outward. These interactions prevent the particles from spreading too far apart, ensuring the rings remain well-defined. Shepherd moons also highlight the interconnectedness of Saturn's system. Their influence extends beyond the rings, affecting the orbits of other moons and contributing to the planet's overall gravitational dynamics. This interconnected web of interactions offers a glimpse into the complexity of planetary systems and the forces that govern them. By studying shepherd moons, scientists can gain valuable insights into similar processes in other parts of the universe. These tiny moons serve as natural laboratories, helping us understand how gravitational forces shape celestial structures on both small and large scales. A closer look at composition. What are Saturn's rings made of? Saturn's rings are a celestial wonder composed of billions of particles, yet their makeup is surprisingly straightforward. Most of the material is water ice, giving the rings their brilliant, reflective appearance. These icy particles are mixed with smaller amounts of rocky debris and dust, hinting at a dynamic history of collisions and interactions within Saturn's system. The water ice that dominates the rings reflects sunlight so effectively that it creates the illusion of a solid structure. However, up-close observations from the Cassini spacecraft revealed the true nature of these rings as vast collections of individual particles. These particles range in size from tiny grains of sand to boulders several meters across, creating a complex and ever-changing environment. Spectroscopic analysis has uncovered subtle differences in the composition of each ring segment. For example, the B ring is particularly dense and bright, suggesting a higher concentration of larger ice particles. In contrast, the C ring contains more dust, which gives it a darker appearance. These variations point to a history of different origins and influences for each ring, shaped by Saturn's gravitational forces and its moons. Interestingly, the material in the rings appears to be relatively pure. This purity suggests that the rings have not been significantly contaminated by interplanetary dust over time, lending support to the theory that they are younger than Saturn itself. The bright, pristine ice also raises intriguing questions about their origin. Were they formed from a disintegrated moon, a shattered comet, or even leftover material from Saturn's formation? The composition of Saturn's rings provides a snapshot of the dynamic processes that shape planetary systems. By studying the distribution and properties of their material, scientists can gain valuable insights into the formation and evolution of not only Saturn's rings, but also other cosmic structures throughout the universe. The mysterious heat phenomenon, rings that glow in the dark. Saturn's rings have long been admired for their shimmering beauty, but recent discoveries reveal a hidden, glowing side to them. This phenomenon, first detected during solar occultations observed by the Cassini spacecraft, shows that the rings emit their own heat. This unexpected discovery has sparked new questions about the forces at play within this cosmic masterpiece. The heat emission is particularly pronounced in the dense B ring. Scientists believe this is due to the way particles within the ring interact and generate friction. As the particles collide and rub against each other, they release thermal energy, causing the ring to radiate heat. This process is more intense in regions with a higher density of particles, creating distinct patterns that align with the ring's structure. Another contributing factor to the heat phenomenon is the effect of sunlight. During the day, the ice particles in the rings absorb solar radiation, which they slowly release as heat during the night. This interplay between solar heating and thermal radiation creates a fascinating cycle that reveals the dynamic behavior of the ring particles. What makes this discovery even more intriguing is the possibility that the heat emissions could provide clues about the ring's age and evolution. The patterns of thermal radiation suggest ongoing activity within the rings, indicating that they are not static but rather in a state of constant flux. This dynamic nature could explain why the rings have remained so well defined despite the forces working to spread their material. The heat phenomenon adds a new layer of complexity to our understanding of Saturn's rings. It's a reminder that even the most familiar celestial objects still hold surprises, challenging us to look deeper and uncover the hidden processes that shape our universe. The faint rings, discovering Saturn's hidden features. While Saturn's main rings often steal the spotlight, the planet is also surrounded by a collection of faint, less visible rings that extend far beyond the familiar A, B, and C rings. These faint rings, including the E and G rings, were discovered using advanced imaging techniques and have revealed a more intricate and expansive ring system than scientists had previously imagined. The E ring is one of the most fascinating of these faint rings. Unlike the dense inner rings, the E ring is composed of microscopic ice particles that are continually replenished by the icy moon Enceladus. Geysers on Enceladus's surface eject water vapor and ice into space, much of which becomes trapped in orbit around Saturn, forming the diffuse E ring. This dynamic relationship showcases the interconnectedness of Saturn's rings and moons. The G ring, another faint ring, is thought to be shaped by the moon Aegeon, which orbits within the ring. Aegeon's surface material is likely eroded by micrometeorite impacts, contributing to the sparse population of particles in the G ring. This highlights how even the faintest rings are influenced by gravitational interactions and the ongoing exchange of material within Saturn's system. Perhaps the most intriguing of all is the discovery of the Phoebe ring, an enormous and extremely faint structure that orbits far beyond Saturn's main ring system. Composed of dark, dusty material, this ring is likely formed from debris ejected by impacts on the irregular moon Phoebe. Despite being invisible to the naked eye, the Phoebe ring is one of the largest structures in the solar system, stretching millions of miles across. These faint rings remind us that Saturn's beauty extends far beyond what we can see. By studying these subtle features, scientists can explore new dimensions of planetary ring systems and uncover connections between moons, rings, and the processes that shape them. Saturn's rings and the solar system's past. Saturn's rings are more than just a stunning feature of the planet. They are a time capsule of the solar system's history. By examining their composition, structure, and behavior, scientists can gain valuable insights into the early days of the solar system and the processes that shaped its evolution. The ring's icy composition suggested a connection to the early solar system, when icy bodies were abundant and collisions were more frequent. These collisions may have played a key role in the formation of the rings, shattering moons or comets and scattering their material into orbit around Saturn. The remnants of these ancient events are preserved in the rings, providing a glimpse into a time when the solar system was still taking shape. Gravitational interactions within the rings mirror the forces that govern the motions of planets and moons. By studying the behavior of ring particles and their interactions with Saturn's moons, scientists can model similar processes that occurred during the formation of planetary systems. The rings serve as a miniature version of the early solar system, allowing researchers to test theories and refine our understanding of planetary formation. Saturn's rings also shed light on the life cycle of planetary systems. The ongoing ring rain phenomenon, where material from the rings falls into Saturn's atmosphere, illustrates how planetary systems evolve over time. This process highlights the transient nature of ring systems, suggesting that Saturn's rings may be a temporary feature in the planet's long history. Understanding Saturn's rings helps us appreciate the interconnectedness of the solar system. They are not isolated structures, but rather integral components of a dynamic, evolving system that continues to shape our understanding of the cosmos. By studying Saturn's rings, we not only unlock the secrets of a single planet, but also uncover clues about the origins and destiny of the solar system itself. That wraps up our journey through the secrets of Saturn's rings, a stunning masterpiece of the cosmos. From their mysterious origins to their dynamic interactions with Saturn's moons, these rings remind us of the incredible beauty and complexity of our solar system. If you enjoyed this deep dive, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest explorations. Until next time, keep reaching for the stars.